So last but not least, we have a talk from Collin Otis, head of perception at Kodiak Robotics, where he was the founding engineer, founded in 2018. Kodiak builds and monitors self-driving trucks, taking commercial loads across the US. At Kodiak, Collin focuses on perception for, and it's cutting off with my Zoom thing, nationwide driverless launch. So I will stop my share, and Collin, you can just take over the screen share and go for it.
All right, thanks a lot for the intro. Yeah, as you said, my name's Collin Otis, the head of perception at Kodiak Robotics. And today I thought I'd talk about how we launch our self-driving truck. So I thought I would just kind of walk through that process, tell how we do things, and in hopes that it would be, I guess, informative. Maybe you would learn something about a self-driving truck program, especially one that's in commercial deployment. And yeah, see if that's useful with folks. So we'll go ahead and jump in. But first, let me just show our truck. I'll get back to this in a minute, but essentially we produce the driver for this truck. And I'll talk about this in a moment in a little bit more detail. But first, let me set up the problem a little bit. So today, there's a huge shortage of truckers. It's an incredibly grueling job. It has one of the highest turnovers of any job in America. It's difficult, long hours. The pay is not great. And so we're kind of over time seeing this accelerate to the point where we're at risk of even greater supply chain issues than we're seeing today. On top of that, it's actually one of the most deadly jobs in the United States, both in terms of the workers as well as the other drivers on the road, because a Class 8 truck can carry up to 80,000 pounds. And so any kind of mistake that's made tends to have a pretty high penalty. So just some stats for you. I can't see the auditorium. I can't see where you are, but I can guarantee that this is true. Look around you, and everything that you see was on a truck at some point. If you're sitting in a chair, if you're using a laptop, the walls, the concrete, sort of every material thing, every physical thing travels on a truck. In fact, about 70% of freight by weight is actually by truck. So it's more than rail, boat, airplane combined. But there's a bunch of caveats to that. So there's about 182,000 injuries every year in the US from trucks on our highways. It ends up to cause about 4,200 deaths. So the safety risk is really, really high today with trucking. It's the 7th deadliest job in America. It competes with things like roofing and logging. It's about an order of magnitude more dangerous than the average job. It turns out that 87% of the accidents that occur are actually preventable, meaning they're due to driver error. And these top 4, I think, are the most important. At the bottom are the things I mentioned, which is there's a shortage of 80,000 truck drivers today. When we started Kodiak 4 years ago, that shortage was only 50,000 drivers. And so this is something that's growing rapidly over time. An interesting stat is because trucking is such a difficult job and people leave the workforce so rapidly, the average turnover for a company employing truck drivers is 100%, meaning they actually replace their entire workforce once over in a year. Now, some drivers will stay for a couple of years, but sometimes they'll actually replace certain drivers twice. Drivers will leave that quickly. So it's a very difficult job to do, and it's also one that's very difficult to keep staffed. So that brings me back to our vehicle. So this is the vehicle that we produce. Essentially what our job is to do is to be the truck driver. And so what that means is we take a vehicle platform. This is a Kenworth T680, but we put it on any platform, and we currently operate on a number of platforms, and we put our kit. And so what our kit is comprised of, on this one, you can see sort of an eyebrow in the center that has a laser and a camera. And then you see 2 mirror pods. And essentially, all that we do is we take a truck off the line, we replace the mirrors, we put this little eyebrow in the center, but you can sort of imagine that those going to the mirrors as well. And we put a computer in the back. And these mirrors are also hot swappable, meaning you can actually change that entire mirror assembly, which is pre-calibrated from the factory you can change that faster than you can change a tire. And so for a vehicle that's needs to be running 23 hours a day for years and years and years, this is actually a really important feature. If you have any kind of issue with your system, you can actually have a untrained technician in autonomy. They don't need to really know much about robotics, and they can just swap out this, and then we sort of warranty the existing unit and fix whatever's broken with it, and then put it back online. So these trucks today operate on public roads across the U.S., always with a safety driver. Many of those runs are disengage free, meaning the safety driver does not touch the wheel. Almost all of our driving miles are operating on commercial loads, meaning we're being paid today to take freight for a very large number of customers. These are the biggest fleets in the world, biggest shipping fleets and biggest carrier fleets in the world. What we do is we put our business model is to put our system on our partners' trucks. And so right now they have a shortage of drivers. Instead of trying to find another driver for certain routes, they'll actually put our system on a truck and then be able to have that truck. We operate as the driver. We also monitor our trucks as well. So that's sort of part of the service we provide. And on the test track today, we pull the driver out. And really the objective of our company over the next couple of years is to pull the driver out, not just on specific lanes, but actually broadly across the United States. So here's the operating model today, which is we have a human driver. We still require a lot of human drivers. So what we do is we sort of automate this longer haul portion in the center. And then we have human drivers who operate at the endpoint and do the more complex sort of deliveries and so on. And our truck takes the most dangerous, most time consuming. It turns out that also is a way to improve the quality of life of human drivers. Human drivers, it has been difficult to hear a lot of the stories of human drivers. They don't get to see their kids grow up. They don't get to see their families every night. It's very difficult to be away from home for weeks or months at a time. And so what we do is we sort of allow folks, which has been where the industry has been going over time. We allow folks to be home every night and to sort of operate in their local area without having to go on these long haul portions. So it's not just our model, but we actually, like I said, run all across the country. And you can see, a lot of announcements over the last couple of years about all the different places that we drive, all the customers that we drive for. And so today I'm going to talk about kind of how do we get there? How did we get there? How do we go forward from here in terms of launching it fully driverless? And so we have a lot of learnings over the last 4 years as we've deployed this system. So just to kind of give you a sense, this is what the freight network, the truck freight network looks like in the United States. These are weighted by the truck volume of trucks per day. So the intermediate lines are 6,000 trucks a day, and the thick lines are 10,000 trucks a day. So this gives you a sense of sort of what is the network in the United States. There are about 4 million Class 8 trucks. Class 8 trucks are the ones I showed you that are the big ones on the title slide there. And our vision for the future is really that each one of these each one of these arteries becomes fully automated. So you press a button, your truck ends up at the other end of wherever you're sending it, and this is just a fully automated thing, and something that is sort of reliable across the entire network of the United States. Maybe to give you also a sense, there's about 40 million total freight trucks, including smaller ones, in operation in the United States. And so one thing that you can imagine is if you can, for example, deploy such a large robotic fleet on the highways of the United States, there's a huge opportunity in terms of automating all of the logistics for wheeled vehicles in the United States and North America and in general worldwide. And so all the way down to kind of the different scales from slightly smaller trucks all the way down to the small ones that sort of deliver locally. And so one of the things to think about is how do we get there? How can we actually focus on this niche of driverless semi trucks, and then how do we sort of build a self-sustaining business? And so I wanted to actually just walk you through the economics of how the business works, just to kind of give you a sense. So here's an illustrative example of how humans actually or robots are paid to drive trucks. So let's imagine you have 10,000 trucks. Each of those trucks can drive 200,000 miles a year. Humans can drive about 100,000 miles a year because they're limited to drive about a little less than half of the day. So the truck has to sit idle for the rest of it. So we can roughly drive double what a human can. And then the rate of pay, we can assume $1 a mile. In general, it ranges from 50 cents to $2. But for this example, we'll use $1. So if you can run 10,000 trucks, there's 4 million operating in the US today. You can generate $2 billion in annual revenue. The trick here is that at 30% margin, this turns into $600 million in annual gross margin a year. And so what that $600 million means is you can continue to reinvest that to grow the network, grow the fleet size, grow the customer count, grow into the other robotics applications for wheeled logistics vehicles, and sort of continue to kind of build up the robotics competency, the perception competency, and all these kind of things. So this is sort of what we're after. And so the question and the thing I want to talk about in this talk is, how do we get to 1,000 trucks? What does that actually look like? How do you deploy 1,000 vehicles, taking freight 23 or so hours a day across the United States, North America, worldwide? And so the first part here is really about the product objective. That our objective is to be able to drive thousands and thousands of vehicles, to have those be driverless. And so how do we get there? Well, the first thing is that network actually matters a lot. This is the AVable, meaning you can actually drive autonomously, mapped lanes that we've announced so far. We actually have a much larger network than this, and we announced these piece by piece. You can sort of imagine where else we might be driving. You can look at a map here of the United States and where the corridors are. And one thing I'll share is that we actually have in the many thousands of total miles that we can operate. We are one of the largest logistics networks that run AVs in the world. And I can tell you, you can actually see our trucks out there. There's people who try to follow them, try to spot them different places. But it's really important actually that you're not just driving in one place if you want to operate a large number of vehicles and keep those vehicles running 23 hours a day. So this is a big focus of us. How do you deploy actually broadly, and how do you actually make the vehicle work broadly? So one of the things is you need to be able to operate in a wide variety of circumstances. So we're going to see more examples, but here's just a couple for you to think about. Operating in tunnels, very difficult clover leaves where the truck can barely fit, or sometimes a truck actually needs to drive off of the road in order to make a clover leaf with a trailer. Emergency vehicles on the shoulder, heavy traffic is sort of just a table stakes. You need to be able to sort of solve in any kind of geometry of road circumstance to be able to merge with the most heavy traffic. And in general, we've been one of the fastest to accomplish this, but there's a huge list of these things that you actually need to be able to do if you want to operate on such a broad network, not do something that's in a sort of one-off or demo in a specific lane, but actually operate a real service. And so I want to walk through the first principles of how do you do this. So the most important thing, as you can see here, is don't hit stuff. And this is where we actually spend all of our time every day. Every part of the autonomy team, perception, planning, prediction, even over to the hardware side, this is really the main objective of our company. The secondary objective is get where you want to go, but it turns out this is actually the really easy part. If you can solve this not hitting stuff, then this last part is sort of the easier part of the equation. So the general rule here is complete the mission and do it more safely than a human. As we build our system, we borrow a lot from the aerospace industry. This is the F-35 coming off the line. And in general, a lot of the testing procedures, when you build an airplane, you don't like just throw it together and then throw it out in the world and see how it does. And when it crashes, you fix stuff. You actually have a much more systematic approach to collecting data, determining the requirements, and then really validating around that. And so there's a well-documented framework that we follow around ISO RSS2262 and UL 4600 that really determines what we call the safety case. How do you systematically build a robot that can execute the mission and meet your safety criteria? And how can you do that in a linear fashion? Not one where you have a lot of time uncertainty, but you can actually understand how to make systematic progress on that journey. So my talk is not going to be about these safety standards, but they're definitely worth learning about if you're kind of working on safety critical robotics. I assume a lot of folks in the room also are familiar with these. So now, how do we get to no collisions? We can launch the vehicle as soon as we've solved all the simulated collisions. This is a broad statement that is really the objective of our program, but there's a lot of details about how you get there. So let me talk about the key metrics that we track. There's a caveat here, which is there's actually a lot more to the program than that. The software side, definitely, and the product is focused on how do you solve every simulated collision. But then there's also a bunch of other things. Policy, hardware, you need hardware redundancy. You have the functional safety standards that I talked about before. You need maintainability, which is where our mirror pods and a bunch of the other things that a bunch of the other things that we have in our vehicle come into play. You need a lot of customers, and then you actually need a really strong operations group to run such a large robotic fleet. But in general, the hardest problem is how do you solve all the simulated collisions? So our key metric is collisions. This is, if you want to solve all the collisions, this is the thing to focus on. And this has the root causes redacted, but what this is a bar chart of specific resimulated collision reasons from simulation for perception. And so what we have here is sort of the focus of our work is actually looking at each of these root causes, really understanding what is the deficiency from a detection, tracking, scene point of view, and then building models, making changes to our software, improving the architecture to really drive these down. These are color-coded by their status. And so there's a couple of statuses. There's something that's still a collision in simulation. We've never had a collision in the real world. A lot of these collisions are sort of hallucinated from cases that we imagine in simulation or from cases that we've observed on the road that are extreme and our safety driver took over. But the other two sections here are near misses and then ones that are solved. And so this is really the thing that we focus on as a program more than anything else, more than any other underlying metric. Interestingly, being safe is more important than getting there. And so one thing that you also have to do, and we've done since the beginning, is monitor our system aggressively and then pull over if something isn't right. It turns out that this is actually extremely important to guaranteeing that you never have a collision on the road. We monitor our system at 100 hertz, and we monitor, there's about 1,000 monitors that run on our system, all the way from hardware to every software process, monitoring inputs, outputs, the health of the software process underneath. What we see here is a snapshot of our vehicle doing a pullover during a fallback on a public road. This one, we actually cut the wire to I believe, one of our lasers. So we can sort of cut things. We can actually turn off the main computer. We can cut any sensor. We can shut down processes, and the vehicle will safely pull over to the side of the road. One of the things that's a secondary objective of the program is how do you not have vehicles that are getting stuck? And so this helps you get to zero collisions, but you really actually need trucks not to get stuck if you want to have an uptime of the service, and also not have trucks that are sort of stranded on the side of the road. And so the secondary key metric that we track is pullovers. What you see here is a breakdown of the root causes for a given month of the pullovers. And these ones are specific to a set of processes in software that we monitor. And what we do is we actually monitor the trend line of this. And this is a very high priority for the team to actually every month take those issues that come up. A lot of times it's from a new process. It's from a new model we've brought online. It's from a new feature we've landed, and really solve those so we don't have pullovers, we don't have failures that happen. Okay, the last thing here is actually you do need to get where you want to go comfortably. So this is an example. What we have shown here is a simulation result of our longitudinal velocity before and after a change. And so the two curves, the white curve and the yellow curve, are the longitudinal velocity of the vehicle from the road data, and then also from the re-simulated road data. So anytime we have a piece of road data that's of interest, we re-simulate that. And then the purple line is after we've solved the issue. This issue is just an example one. I think it's interesting. This is one in very, very heavy rain. So what we have here is very heavy thunderstorm in Texas, and a semi is passing us to the left and also throwing up water in front of the vehicle. And so it throws up a huge wall of water that basically blinds all the LiDAR. It partially blinds the camera. It doesn't blind the radars. And so what we had was a lot of work to really understand this, check against the different sensors that we have, and be able to continue to drive safely without slamming on the brakes in the rain. The first time we drove it, we actually braked pretty hard for that wall of rain. And so that's a pretty uncomfortable event. It turns out that comfort is also important for other reasons. If you slow down too quickly on the highway, you'll actually result in collisions. And so comfort and collisions are not totally unrelated. This is the key metric that we track there, which is called ride quality. What we do is we track ride quality events. So here, what you're seeing is the green line is the total number of ride quality events. And then we actually track all of the breakdown of the different types of events that we have. And this is on a weekly basis. Examples of those event types are a false positive blinker, a time when you, for example, might think that you have a vehicle on the shoulder at 250 meters ahead, and you put on the blinker, but it turns out you get 50 meters closer and the vehicle's not there. Brake taps, significant overbraking like the one I showed you before, where you have, especially in bad weather, you have something that happens that causes you to slow down dramatically. And there's a list of other things that we sort of track over time. One thing that is worth mentioning on this one is there's a couple secondary reasons why comfort metrics are actually important. We have safety drivers in the vehicle, and until we launch, we actually have to make the ride tolerably comfortable for a safety driver to be in the vehicle every day. And so one example of this is high jolt events are not okay for humans, but oftentimes they're okay for a vehicle. For example, if you want to sort of tap the brakes quickly so that you can begin to grab the caliper in order to delay and sort of to increase your ability to stop quickly, this is fine for a robot. It's fine for the freight actually in the back, but it's not fine for a safety driver. And so we have to balance that road to driverless. There's another thing, which is we can actually brake freight if we brake too fast. So one of the nice things about self-driving vehicles is that, self-driving logistics vehicles is that freight doesn't complain as much as humans. One of the real difficulties in robotaxi is, as many folks are probably aware, the ride quality has to be pretty good. You have to actually beat a human in ride quality. That turns out to be pretty hard. In trucks, you don't have to do that. But there is an extent to that where if you can actually brake the freight, especially for liquid stuff in the back that's containerized, let's say like a huge container full of pop that's in metal cans, that stuff's actually pretty fragile, and you don't want to break that. So that's another thing that we have to really keep an eye on pretty closely. All right, so now for the most interesting metrics, which are the development metrics. I talked about the program metrics, the product metrics, and then sort of our key metrics as a company, but really you don't do work against those. You don't like make changes to the software and sort of test it against those broadly, except for collisions. So I wanted to walk through a number of different things. Before I do that, I want to say that the objective here is collision. And so note that our system is tuned to avoid collisions, not to maximize scene likelihood. A lot of the work that is done sort of on open data sets and things like that is to maximize likelihood. It turns out that's not the right thing for a self-driving vehicle. The right thing is you want to maximize the recall of the actuation. So what do I mean there? let's say that there's a pedestrian in the road, and you would like to slow down or stop for that pedestrian. It actually doesn't matter that you can exactly track that pedestrian closely. What really matters is that you can detect that it's there, you can begin to slow down the vehicle, and that you don't collide with that pedestrian. And so what you want is the recall of that actuation. And so the system, especially the perception system, and then the planning system along with it, is tuned to sort of maximize that response. And the reason for that is that edge cases are actually much, much more important than average driving. And so what you want is you actually want to do the right actuation in these incredibly rare cases, rather than be overall good from on the average point of view. So before I jump into the actual metrics, let me just talk about how the development cycle works. In our system, we essentially have two set cover problems. So the first one is the set cover of scenarios. You essentially need to collect scenarios, which are like events. They can be a minute, they can be a couple minutes long. They're things that can happen in the world, and including environmental conditions, that are comprise the total set of things you will ever see. You could sort of think of this like, these are all the cases that you need to be collision free on. And so part of the objective, and this is actually, I would say, equally challenging to solving them, is actually collecting them. How do you collect such a huge corpus of data so that you can actually show that you can solve them? And so there's a lot of ways to do that. There's a lot of tricks. I won't talk about too many tricks this time, maybe on another talk, but in general, you can imagine them, you can actually see them, you can simulate them digitally, you can mutate a digital representation, meaning like you can, of course we do sensor simulation, but you can also take like real sensor results from the world, and you can sort of mutate your position in the world. And then you can go simulate them physically. This is really useful as well. This is where you actually go to the track, you set things up, you stage a scenario, especially for very extreme scenarios. This is one that's really useful and is kind of the last place that you show that, yeah, I was able to prevent that collision for that very extreme case. So that's the first set cover problem. How do you get all the scenarios? The second one is, how do you solve all the things? And so you actually then need to take all those scenarios that you have, and you need to show that you can solve them in simulation. And you have a secondary thing, which is actually to show that the simulation matches reality. So there's some interplay there between the two. The development cycle goes something like this. You design and build against the requirements that come from those scenarios. You evaluate on all the things that you had in the past, all your corpus of scenarios. You then deploy, usually for production loads is what we do, after you've kind of passed all of those tests. And then anything that happens on the road or in your structure testing, or you'll start to imagine more things over time as you get inspired by what happens on the road. You then actually re-simulate all of those events, and you auto-analyze the disengages. So on item 4 here, let me give you an example. Anytime our driver touches the wheel or leaves any kind of comment for us, that immediately gets re-simulated. And then we run a lot of auto-analysis on that to figure out, was this a comfort issue? If so, what was it? Is it a collision? Is it close to a collision? We run a lot of the perception metrics that I'm going to talk about later. We run a lot of those and figure out, well, where did perception fail? Does it matter that it failed? Does it not matter? And kind of how do we route that for future work? And then item 5 here, we immediately add it to the evaluate set. So the evaluate set really grows over time. When we deploy, our process is visualized on the bottom there. When you deploy code, one thing that we like to do is, for example, any new candidate that joins our team, they're typically deploying code within a few days, and definitely within a week, they're deploying code out to the fleet. That code initially goes through our evaluation process and then lands on what we call the daily release. This daily release gets a limited number of miles, and it runs a limited number of extra sims. Then after it's doing well on daily, it'll get promoted to candidate. In candidate, you'll actually drive a much larger number of miles. You'll start to traverse states. You'll start to go across state borders. And then you'll run a huge set of sims that take sometimes days to run. After your code has passed candidate, it will then get deployed on our stable branch, which will start to do production loads. So we will there you're open for nationwide deployment. This can take, getting from daily to candidate, or daily to candidate can take a couple of days. Candidate to stable can take a couple of weeks, sometimes a month, depending on how things are going, depending on how good the change is really. And then we run our whole body of sims against those stable changes. So when we discover and test different scenarios, like I said, there's actually three important things: on-road testing, simulation, and structured testing. These are all important methods for getting that scenario coverage that is really important for being able to launch the vehicle. Here's an example of why road testing is so important. When we started Kodiak, we did not have any houses in our data set. So what you see here is something that we've seen 28 times just in Texas in the last year, which is a house being transported on a trailer down the highway. That's 28 times on the road. Oftentimes the houses are stopped on the side of the road. I actually don't know why. I don't know if the house breaks down or what happens here, but you actually need to be able to detect and maneuver around these things. Many times these houses are actually taking up more than one lane. And this is something that we definitely did not imagine when we started the company. And that's why road testing is actually really important. We see new things every week. And so the really critical thing here is, how do you not miss seeing the house? Like, you can never miss a house. And when there's something new that surprises you, you have to make sure that you never miss that thing. And so all of our work is geared around that. I wanted to take a little pause here and look at sort of state-of-the-art metrics. On most of the data sets, we look at AP, and that's usually IOU-based AP. And one of the difficulties is, if you're looking for houses and you want to guarantee that you have a model, let's say a camera or LiDAR model that solves all the houses, in general, these are incredibly rare. IOU isn't necessarily a great measure for them. Houses come in all different shapes and sizes. In general, it's a very hard objective to learn. And it can really get hidden by your metrics. Philip Kronbuhl gave a good talk at CVPR last week, in which he showed this, which is center point. This is center point, which is a LiDAR detection model. And it shows the degradation with range. And you can see that the MAP goes all the way down to 37. This is an IOU-based MIP for the 30 to 50 meters, which isn't even that long of a range. And so what we need is metrics that actually make sure that we still have our requirements met at any range, and sort of capture these cases that we care about a lot. Here's a typical example of why IOU-based AP is not enough. This is just cruising down the highway, and I want you to focus on that long range out there. It's very difficult to even see in our wide camera. But what's going on out there is there's actually a car in our lane at 357.22 meters. That's shown in red here. Let me zoom in on that one. So the yellow is the track of that car. The orange there, or brown, is a radar detection of that car. Inside of there's actually one radar return. That radar return is not even inside the track. And but in general, this case is actually solved very well. It's actually really important that we plan around this vehicle. That's what that purple gate is. That purple gate is sort of it's an optimization gate for our planner. And so this one is really not captured by IOU-based AP, average precision. Just to maybe drive this home even a little bit more, in that same scene, here's a semi that is in our lane at 1,004.39 meters. And this one is definitely not captured well by AP. We actually have a single camera that's detecting this. We don't even have a dual camera on it. So we have a single camera that's sort of giving us that detection. And it's not necessary for us to actually be able to see stuff at 1,000 meters. It's useful, but it's not super necessary. And so this kind of drives home the point a little bit more. This thing could be wrong by many tens of meters, and that's not really a problem. So what do we do as an alternative? What we do is we optimize specifically the things that matter to avoid a collision. And so the first thing is just collisions. This is why having a huge data set is so important. We collect all of these things, and actually when we're working on any feature, we go and run a large set of them, or sometimes even a small set. This is an example of inside of the simulation tool that we use, which is called Simian. This is an example of trying to improve on a set of cases with some very odd-shaped vehicles, in which we have a single failing collision, and we're trying to sort of solve that collision without regressing any of the other ones. we run our perception metrics underneath this, but this is actually, if you want to optimize for collisions, you can actually just optimize for them directly. And this is the most important thing when we make any change to the software, is to be able to actually do this on a real-time basis to figure out how many collisions does your change have. Another metric that is really useful is what we call it recall, but really it's around like existence. So the way I say this is, did I miss anything? And so what we do here is we compute the recall of all the detections, the sensors data, all the data from all the sensors, and all the labels. And you can actually compute a metric, which is the recall of all the things. As I go through the rest of these metrics here, note that many of these metrics are actually combined. You can imagine how these kind of get combined and so on, because I'm going to talk about regions of interest in a minute. But what we do is we basically make sure that our tracks are the output of the perception system that's tracking all the vehicles, that it sort of covers all of the data that it saw, especially in the regions of interest. And so this is a really important metric for us, sort of to explain all the data and to explain all the detections. Another important metric is, instead of IOU, especially for long range things, we use the range to the nearest point, precision, and recall. And the inspiration here is that this is the thing that really matters for you to see and avoid. So what this is the error against the ground truth of the nearest point on a vehicle versus where you said that vehicle was. Because this is the thing that actually determines whether you can brake in time. And there's another thing we do here, which I'll talk about in a minute, which is we actually can evaluate this over a period of time, because it turns out that dynamics matter a lot. This is, I think, something that is really necessary for solving the problem, but not super well addressed in data sets, which is, how do you sort of estimate the velocity and acceleration? How do you think about that? And how do you evaluate that? And so you can actually evaluate sort of the position or this range point over 500 milliseconds is one way to do that. We also sort of look at the knowledge of a thing being there. So there's some distinction there. It's like, can you recall the motion model of that thing? So do you know the right motion model? Because the right motion model is actually really important for actuating around it. And again, this goes back to the inspiration of, you want to figure out how do you actuate against it. This vehicle that I was pointing at is about 100 meters away. We don't have great IOU on it, but we have a really good velocity and acceleration estimate, and we have a good range on it. That vehicle pulls out in front of us, and we actually estimate that really well. And so this is, kind of how we use that range metric on cases like this. This is an example for one of our networks. This is range from 0 to 310 meters, and we're showing the absolute max range error, and I think P90 or P99 or so, sorry, 99th percentile or 90th percentile of the range error. And what you see here is sort of, how does that change over time? How does that change over the distance? It gets a lot larger. You can see that we sort of prematurely range things too close to us. That's that crooked line on the bottom. And this gets much worse as you go further out, which is sort of what you expect. But again, this is very tolerable when you're trying to drive a robot. Range uncertainty at a long range is not a problem. You have time to react to that. Another thing that's really important is data segmentation. So we run all of our data operations on segments of the data, and it's important to understand how you operate in each of those. It's also important that that's covered by the data. So here's a bunch of things: merges and interchanges, construction, heavy traffic, vehicles on the shoulder, harsh weather, driving at night, driving with no lane markings, unusual vehicles, lane change aborts, cut-ins, aggressive driving, reckless construction workers. These are all separate data sets that are important to evaluate, and the requirements that you put there are actually different. For example, for a reckless construction worker data set, you're actually driving a lot slower, and so the requirement on the vehicle is a lot different. Okay, number 5, near range. How do we do near range? And here is the good news. Our favorite is back, which is IOU MAP. So this is the metric that's on every data set out there. And we use this one too. It turns out in the near range, this is very, very useful. But we do it with a twist, which is 500 milliseconds dynamics, or sort of interpolation of this. And so here's an example. This is a vehicle that's passing us to the right. It's sort of just in a lane there, well behaved. And if you just look at AP here, it's actually relatively good. We get the bounding box around the vehicle very well. Well, it turns out that what happens in the next a few seconds is that vehicle moves laterally very quickly. It has a high lat jolt, then it has a high lat accel, crosses the white line, and then slams on the brakes in front of us. And so 500 milliseconds extrapolation of a track, and then sort of looking at how that matches with the labels. This incorporation of the dynamics lets us capture the whole set of the state variables that matter in the near range. And so this is sort of the twist that we do on MAP. I think this is the last one, which is comfort. Like I said, comfort matters a lot. This is an example of an abysmally failing change, which was not released. So what you see here is you see a white and red line. This is the speed over time. And what you see is a change that we put in. This is only over 250 seconds of a simulation. And that change causes us to command speed drops that are really dramatic, all the way from 25 meters a second down to 5 meters a second. And that's because a bunch of false positives were introduced. And so this is something we monitor really closely, the speed drop. That's a really good indicator for how comfortable is the ride. And it's something we measure really closely. So just in closing, I know I'm at the end of time here. We talked about three things: the product objective, which is to launch thousands of trucks; the key metric that rolls up to that, which is really the number one for us, is collisions; and then some of the development metrics that we use as precursors to collisions that we can actually use to evaluate software changes, model changes, and so on, specifically inside of perception. And so there's a couple of takeaways here. One is that focus on specific metrics goes a long way. You can actually waste a lot of time if you have the wrong metrics and you're optimizing them. The vehicle can actually get no better. One thing to focus on is, how can a metric be gamed? How can you get better at a metric, but the vehicle still drives worse? We think a lot about this. We think in a very adversarial fashion against our metrics. The metrics are really driven by requirements. They're also driven by your approach. Different metrics will differ. Different approaches will require different metrics. And the last one here is that data matters a lot. So our corpus of scenarios is really our lifeblood for development. And this is something that's extremely important. The last thing I wanted to call out here is that as we develop vehicles broadly for a bunch of use cases in the industry, we may need data sets and metrics that are more tightly coupled to the use cases of those vehicles, especially as we think about range and highway and different types of vehicle sizes and types. There's a limit to how much some of the generic data sets that we have out there can be useful. So I'm not going to end my talk this way, which is making a pitch for Kodiak. I'm not going to end with putting my email address there and saying I'd love to hear from you if this is the type of work, fielding robots across the country, that's interesting to you. Instead, I'm going to thank you for the work that you do. We read the papers, we watch the talks. Everything inside of our robot was essentially developed by the community. And thank you for all the work that you do. It is what makes up our robot. And with that, I'll end. Thank you.